Welcome to physics. In the mechanics, when a lever is at rest and not moving, we consider it as an object in equilibrium. Imagine a girl carrying a cat standing in a lever and her teddy bear on the other side of the lever. If the lever is not moving, then we consider the lever as an object under the state of rotational equilibrium. How do rotational equilibrium occurs? Let us call John to explain.
Rotational equilibrium occurs when an object is not rotating and remains at rest. All torques acting on an object have a net value of 0, and there's no rotational acceleration. Suppose a bear wants to balance himself in the part of the wood which is not supported. If the bear successfully balances himself in the wood, how can you explain it? Let us go deeper. To explain, recall that we describe an object or body which is not moving using the law of inertia. Law of inertia explains that if the forces acting upon an object are balanced, then the acceleration of the object will be 0 and tends to stay at rest. Same is true for rotational motion. If the forces acting on an object is balanced, then a body will not rotate unless acted upon by force. F net is not equal to 0. F net is 0. Note that we define force as the one which causes the bodies to accelerate or move. In rotational motion, torque takes the place of force. Just as force is that which makes objects accelerate linearly, torque is that which makes objects accelerate rotationally. Torque is defined as the cross product of force denoted as F and lever arm denoted as R and sine of the angle between lever arm and force. Thus, we can have the equation, torque is equal to Rf sine theta. In the equation of torque, what does the R represent? Alice, can you please explain it?
Sure, John. In the equation, T is equal to Rf sine theta. R represents the lever arm. Lever arm is the effective distance from the axis of rotation to the point of force. Consider the diagram. Let A is the point of rotation, the R is the length from A to the force. Given the diagram, the torque equation is obtained. In this diagram, the angle is 90 because the force is applied perpendicularly. Note that force is not always applied perpendicularly. If the force is not perpendicular, then just remember that the angle we take is the angle between the lever and direction of force. Center of mass. The center of mass is the point where all of the mass of the object is concentrated. When an object is supported at its center of mass, there is no net torque acting on the body and it will remain in static equilibrium because the summation of torque will produce a 0 value. If the center of mass is within the actual structure, then therefore we can say that the body is stable. George, can you please continue?
No problem, Alice. However, if the center of mass is outside the actual structure, then therefore we can say that the body is not stable.
Thank you, George. Consider the Leaning Tower of Pisa. The Leaning Tower of Pisa is still stable because its center of mass is still within its structure. If the tower is leaned more and more, its center of mass will be outside, making it unstable. Before we begin examples and calculations, let us summarize first the conditions for equilibrium. Conditions for equilibrium. First, a rigid body must achieve a translational equilibrium wherein the summation of the forces acting along the x is 0 and forces acting on the y is 0. Second, the rigid body must also be in the state of rotational equilibrium wherein the sum of all torques is equals 0. Overall, an object is in equilibrium if it is in the state of rotational and translational equilibrium. Isa, can you show them an easy example?
Let us practice a simple example. Suppose we have a uniform, horizontal beam and we are asked to calculate the tension in its cable. Consider the illustration. Since the beam is a rigid body, we must satisfy all three of the following conditions if we wish to place it into the state of complete equilibrium.
Drawing the FBD of the illustration, we will have this. If the pivot is placed at the hinge where the beam meets the wall, H, V and T cosine 30 have no moment arms since they pass through the pivot. Thus, the equations are: to solve for tension we can use the summation of forces. Summation of Fx is equal 0. H is equal to T cosine 30. Summation of Fy is equal 0. V plus T sine 30 is equals the mass multiplied by the gravity. Mg represents the weight of the beam. Therefore tension can be calculated as T is equals H over cosine 30. Or T is equals mg minus V over sine 30. Thank you, Aisa. Let us go to more challenging examples. If you are not ready, you are free to pause the video. Rotational equilibrium sample problems. Find the tension in the rope attached to a beam. The 10-meter beam is weighing 200 newtons. The rope is 2 meters from the right end. Another object is attached weighing 800 newtons at the right end of the beam as shown in the figure. Free body diagram of the beam is shown. Computing for the summation of torque, we will be using point A. Using the formula summation of torque at point A is equal to 0, the solution will be summation of torque at point A is equal to 0. 0 is equal to torques of all the object acting on the beam with respect to point A. T is the variable for the unknown tension. T will now be equal to 2,250 newtons. Let us proceed to the second example. A 6 kg cat is sleeping on a uniform plank of length 3.0 meters, and mass 9 kg, that is supported by sawhorses a distance 1/3 length from each end as shown. Assume the center of mass of the cat is a distance 1/6 length from the end of the plank. Find the vertical support forces F1 and F2 that each sawhorse exerts on the plank. Hint: apply the torque equation around an obvious point to find F1, then use the force equation to find F2. Let's apply the torque equation around the right-hand sawhorse contact point. Torque net inward is equal to 0. In this example the angle is 90, so sine 90 is equal to 1. So the equation is 1/3 length times F1 minus 1/6 length times the mass of the plank times gravity plus 1/6 length times the mass of the cat times gravity is equal to 0. Substituting the values, the magnitude of F1 is equal to 14.7 Newton or 15 Newton in correct significant figures. Now apply the force equation. Force net up is equal to 0. So the equation is F1 plus F2 minus the mass of the plank times gravity minus the mass of the cat times gravity is equal to 0. Substituting the values, the magnitude of F2 is equal to 132.3 or 1.3 times 10 to the second power Newton in correct significant figures.